Hello everyone, I'm Wu Junwei. It's a great honor to be here to introduce our work. Today my representation is about performance analysis of graph neural network frameworks. The data in the task targeted by the previous deep learning algorithms are typically represented in the Euclidean space, such as images, text, and videos. However, there is an increasing number of applications where data are generated from non-Euclidean domains and are represented as graphs. Therefore, graph neural network is rapidly developed to deal with complex graph data. With the development of graph neural network, many graph neural network frameworks have appeared. In consideration of the existence of various GNN frameworks, it's necessary to evaluate the performance of these frameworks in the implementation of GNN models. Currently, the existing studies related to GNN models mainly focus on the effectiveness of different GNN models on domain tasks. Therefore, our work mainly focuses on the performance characteristic of the GNN frameworks. Graph neural network is meaning to that the nodes in the graph update the features by learning the features of neighboring nodes. Figure 2 depicts the process of node feature learning in the process of graph neural network training. The process can be divided into two stages: aggregation and update. In the aggregation stage, nodes aggregate the features of their neighbors, and in the update stage, nodes update their all features according to the features of their neighbors. Equation 1 and 2 are the formulas of these two phases. In our work, we select Deep Graph Library and PyTorch geometric as our performance evaluation objects. Currently, there are many graph neural network frameworks, but DGL and PyG are the most popular and natively perfect. Most of the research works use PyG or DGL when it comes to using graph neural network frameworks. The realization of these graph neural network frameworks is based on the currently mainstream deep learning frameworks. PyG framework only supports PyTorch, and DGL supports PyTorch TensorFlow and MXNet none. PyG only supports the PyTorch framework, so many operations can directly use the more efficient API provided by PyTorch framework, and DGL supports multiple deep learning frameworks, so many operations are implemented by themselves, which may affect the performance of DGL to a certain extent. We select 6 popular GNN models to evaluate the performance of the frameworks. These models are mainly different in how to update their old features. So the features of neighbor nodes. For example, the first 3 models treat their neighbor nodes equally when learning the features of neighbor nodes, where the later 3 models use special mechanisms such as attention mechanism and gating mechanism to differentiate the learning neighbor nodes feature. Our work considers 4 performance metrics: test accuracy, training time, memory usage, and GPU utilization. Next, let me introduce some of our evaluation results. Table 1 and Table 2 show the performance of GNN models in node classification and graph classification tasks, respectively. From the experimental results in the tables, we can see that the two frameworks have no obvious advantage or disadvantage in test accuracy, but the DGL framework is obviously inferior to PyG framework in training time performance. So we evaluate training time breakdown and detailed levelized execution time of the 6 models in the 2 framework. In Figure 3, we show the execution time breakdown for 6 models with different batch size across these 2 frameworks on dataset enzymes. As we can see from the figure, data loading time takes up a larger proportion of total training time. Currently, the computation of the graph neural network is lightweight because when the graph neural network has too many layers, the features of all nodes tend to be similar. Therefore, the data loading stage is easy to become the training time performance bottleneck. What's more, on dataset on enzymes, as the batch size doubled, the forward and backward propagation time nearly halved. However, Figure 4 shows the execution time breakdown on dataset DD. In this figure, as the batch size doubled, the forward and backward propagation time is only slightly less, or even larger. In dataset DD, the average number of nodes and edges of graph and the dimensions of nodes features are significantly larger than that of enzymes. It can be said that the parallelism of GPU is not well utilized when training the graph with many nodes and edges, and the strategy of GNN training on the big graph is worthy of further study. What's more, the data loading time of DGL is significantly longer than that of PyG, which mainly results from the time cost of data processing. The data processing operation models a batch of graph as one big and disconnected graph. In Figure 5, the training time of each layer across these 2 frameworks is presented. Compared to PyG, layers of all models provided by DGL are more time-consuming. This is mainly because layers of models in DGL mostly use more operations. For example, in GCN, the node features are normalized before and after updating in DGL, and the node features are only normalized before updating in PyG. What's more, the pooling operations provided by DGL, which get the features of graph by the features of nodes in the graph, are also more time-consuming than these provided by PyG. In PyG, the pooling operations are based on the scatter API of PyTorch, and in DGL, the pooling operation is based on their segment reduction operator. Figure 6 shows the memory usage of models with different batch size for 2 frameworks on dataset enzymes and DD. In most cases, the memory usage of models implemented in DGL framework is more than PyG framework, and on big graph, the memory usage of anisotropic models will increase significantly and is significantly higher than other models. The anisotropic models refer to the previously introduced models that use special mechanisms to differentiate learning label nodes, such as attention mechanism and gating mechanism. In Figure 7, when training models in the 2 frameworks, the GPU utilization is pretty low. As we said before, data loading time will be a major time spent in training, which also leads to the low GPU utilization. Figure 8 presents the time cost per epoch of multi-GPU training for GCN and GAT. The implementation of multiply GPU training of these two frameworks is based on the multiply GPU training provided by PyTorch. At present, the performance defect of graph neural network training mainly lies in single GPU training. In conclusion, our work performs a comprehensive evaluation and analysis to understand the test accuracy, training time performance, GPU utilization, and memory usage of models in the frameworks. From our experiments, models in the two frameworks have similar statistical test accuracy, but the training time performance of models in DGL is significantly worse than that of PYG. The data loading time is a major part of training time, which also leads to the low GPU utilization of GNN training in the two frameworks. GNN models don't make good use of the parallelism of GPU training. The internal and intra-node parallelism of GNNs deserves further study. Okay, that's all my presentation. Thanks for your listening.